Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Application of Additive Manufacturing Methodology in Legacy Parts Mahesh K. Scient Ltd., Hyderabad Bassetti Chandrasheker Scient Ltd., Hyderabad Lasheer Mohammad Scient Ltd., Hyderabad Abstract. The future of successful technology is to adapt to the key mass customization of the product, which needs to use the latest manufacturing processes. This reduces the project cycle time, as it takes more time to plan and then execute. The manufacturer needs to be agile. Conventional machining, which can be described as subtractive, material is gradually removed from the stock. Conventional manufacturing processes impose constraints on the design and can hence be described as design driven by technology. Additive manufacturing, AM, on the opposite hand, is often described as technology driven intentionally. Manufacturing any complex design without technological constraints is possible in AM. But the limitations in AM technology are the repeatability and the effectiveness to produce critical areas without impact to the desired design profile. Also, the validation of the structural properties concerning design is a limitation in additive manufacturing technology. There are various types of additive manufacturing methods used for getting the desired properties of the gas turbine engine parts. The cons aspect of additive manufacturing is its adaptability to production thanks to its repeatability. This paper presents design optimization of the parts produced by additive manufacturing using the latest technologies available today, such as like solid thinking, Inspire, Optistruct, Materialize, software. The paper addresses all these parameters in design for additive manufacturing using the latest software. A case study is presented by Redesign a bracket in gas turbine engines. This paper also has discussed the significance of the identification of cost-driven features and material/powder selection during the preliminary/conceptual design phase of gas turbine components. Keywords: additive manufacturing, selection, product life cycle, material/powder. Introduction. The 21st century industrial revolution depends mostly on the rapid customization of the design. The market trends show companies need rapid design changes to the product to sustain in the market. The rapid customization of design is only possible if we have a manufacturing process that has very little manufacturing time. But to accommodate the change in designs rapidly, the tools used for the manufacturing also require customizations to their features as per the requirements. The manufacturing lead time for legacy engines and engines under development is the major emphasis for meeting the incorporation date for gas turbine engines. Most of the aero companies are working on technologies which can improve the efficiency of the gas turbine, which can be done either by having altogether new technology like GTF technology and by possible weight reduction. In the aerospace industry, weight is of great importance to the engineering design of the legacy engine components and also under development engine components. Complex parts manufacturing requires a lot of skilled labor when we go for a conventional manufacturing process. Meeting the schedules is critical nowadays to meet the change in designs to decrease the product cost. Decision on the design of a product influence the lead time for the component, cost of the manufacturing tools, e.g. the method of manufacture of the design will affect manufacturing cost. Traditionally, the design has to pass from various iterations that involve designer and analyst. This design process is the time taken where a designer sends design geometry to the analyst and then the analyst runs his analysis and sends feedback to the designer. This process is repeated until a valid design meets the analysis criteria. The final design is then handed to the manufacturing team, which then may have additional constraints or concerns, and iterations can continue. 3D printing and additive manufacturing coupled with various optimization technologies, like topology, allow the designand analysis and manufacturing iterations to be reduced significantly. The below figure depicts the selection of technology based on complexity and volume. Fig. 1. Strong cost advantage for complex components. Fig. 2. Strong cost advantage for small volume production. IJERT 10 is 060013 www.ijert.org 124. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 2. Background 4. Additive manufacturing. The competitive moves observed in the last 2 decades were the lead time for manufacturing, evolving from a cost-plus margin paradigm to a market-driven one. This has thrown a real challenge to the strategic sourcing team to create healthy competition among potential suppliers. Making a good choice on the changes after the product is manufactured will be a tough task. To get reasonable quotes, the strategic sourcing team needs to be familiar with time-driven features, specific manufacturing processes, and materials cost. Sometimes taking control of material, simplifying the complex feature will result in huge cost savings. One solution to these problems is additive manufacturing, which reduces the lead time of the product with quick customizations to design. This reduces the cost based on materials, labor, overheads, and increases the profit margins. There are many additive manufacturing methods like powder-based metal additive manufacturing processes, binder jetting, direct metal laser sintering, DMLS, additive manufacturing processes for complex parts available in the market. This paper concentrates on the powder-based metal additive manufacturing processes and validation methodology for gas turbine parts using Inspire and Optistruct softwares, and in addition, it also helps in the understanding of high-stress and low-stress areas for optimized design. 6. To ensure that the part will perform as simulated, a mid-stage validation is conducted on a uniform part before creating the ultimate products. Manufacturers found that the planning of the design based on the manufacturing process feasibility is very essential for the successful development of the design. A design that has no manufacturability is difficult to be manufactured. So, to overcome all these hindrances, we need a quick prototype of the object being selected. 3D printing, or additive manufacturing, AM, manufacturing process is thus selected with more design flexibility. Additive manufacturing now enables both a design and industrial revolution, in various industrial sectors such as aerospace, energy, automotive, medical, tooling, and consumer goods. The use of additive manufacturing, AM, with metal powders may be a new and growing industry sector, with many of its leading companies based in Europe. It became an appropriate process to supply complex metal net-shaped parts, and not only prototypes, as before. 7. A selection of part for metal additive manufacturing process. With the current development in additive manufacturing, the production of all the parts by using this technology is not feasible and not cost-effective. Cost is one of the main parameters in aero engine production. The factors which drive the selection of the components are given in below figure. A. Complexity of the part, include size and shape. B. Customization required. C. Functional integration. 3. Topology optimization. Structural optimization deals with the assembly of material to sustain loads in the best way. It has been used in multiple areas of applications too. Problems of structural optimization have been modeled and solved using size, shape, or topology optimization. Topology optimization, also known as layout optimization, is a mathematical tool which seeks optimal material layout within a given design domain for a given set of boundary and loading conditions. It determines connectivity, geometries of cavities and void locations in the design domain. 3. The base of topology optimization date back to the late 1980s. This is an iterative process that determines the best arrangement of a limited volume of structural material within a given spatial domain to obtain optimal mechanical performance of the design concept. Benso and Kikuchi first introduced this computational technique for the optimal distribution of material in continuum structures. The comparative study on stress and compliance-based topology optimization was performed by Schiemels and Endiga 5. The objective of the problem discussed in this paper is to achieve minimum mean compliance with a constraint on the available mass, or volume, and it is intended to explore the role of topology optimization in AM to design a lightweight model. Fig. 3. Steps involved in metal additive manufacturing process. Below steps are involved during the selection of aero engine parts which is suitable for a metal additive manufacturing process. A. Size of the component. Currently, this technology is explored up to only the part size of 450 mm all around and height of 1500 mm. B. Enabling a completely new design approach. C. Resolving the constraints of conventional manufacturing. IJERT 10 is 060013 www.ijert.org 125. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 D. Leading to completely new solutions, E.G. Move from metal to plastic, making a part lightweight, yet functionally, new design not possible with conventional methods. F. Material to be used. Currently, only a few nickel-based and Ti-based material are qualified for the use. G. FAA, Federal Aviation Administration, Certification B. The overview of metal additive manufacturing processes. 3. HU investment. 4. FAA certification. The certification process for the components produced by this method still has to mature. V. Some of the undercuts in the parts where support is not feasible during AM process. Below figure shows actual manufactured part using a metal additive manufacturing process. 10 Metal additive manufacturing technologies offer many key benefits. More design freedom versus conventional machining. 2. Integration of end customer into design process like complex internal channels. 3. Fast prototyping through flexible and fast design adjustments. 4. Mass customization. V. The unique use of lattice design can be useful to reduce the use of material or can be used where it is required without any constraints. 6. Net shape process means less staple consumption, up to 25 times less versus machining. 7. Reducing assembly and disassembly operation by using net shape capability helps creating complex parts in one step. 8. No tools needed, unlike other conventional metallurgy processes. 9. Short production cycle time. Complex parts are often produced layer by layer during a few hours in additive machines. X. More cost saving by reducing the use of raw material in the case of expensive or difficult to machine alloys. Below figure shows the mapping of metal powder additive manufacturing technology. Fig. 5. Bracket designed using additive manufacturing technique. V. Design optimization for AM technology. A. Introduction. To take full advantage of AM design possibilities, it is important to redesign conventional parts. Design optimization can be done in several directions. Reduce the total number of parts. Design for functionality. Design parts to be multifunctional. Lightweight topological optimization. Design for ease of fabrication. B. Case study. The example below shows a redesign case study of a bracket at reducing drastically the total weight using various AM software. Fig. 4. Mapping of main metal powder additive manufacturing technology. C. Constraints of metal additive manufacturing process in aero gas turbine. I. Availability of the material. Chemical composition. 2. Part size. Fig. 6. Initial geometry of the model. IJERT 10 is 060013 www.ijert.org 126. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Loads applied. All DOF for bolt holes 8,000 pounds. Load in X, Y, Z direction. Table 2. Boundary conditions applied for the case study. Fig. 7. Geometry of the model after weight optimized. Inspire Optistruct software was used to optimize the design and make the bracket suitable for additive manufacturing technology. Fig 9. Kinematic couplings are used between bolt holes with reference point in order to simulate bolts and at the clevis location for applying load. Fig 8. Optimized geometry from Inspire software. Fig 10. Bolt holes constrained in all DOFC material properties: material yield strength, at room temp, ultimate tensile strength, at room temp, Young's modulus, Poisson's ratio, density: titanium 128 ksi 138 ksi 16500 ksi 0.3420.16. Table 1. Material properties of case study. Bracket note: used the same material properties 8 for initial geometry and for weight optimized geometry. D. Boundary conditions, optimization algorithm, objective function constraints, method of moving asymptotes, default value, kinematic coupling between bolt holes. Fig 11. Load of 8000 lbf is applied in global X, Y, and Z direction. Note: boundary conditions and loading is the same for both the models, and above are the pics corresponding to the initial geometry. 9. IJERT 10 is 060013 www.ijert.org. 127. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org. International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181. Volume 10, Issue 06, June 2021. ESMAX principle: structural finite element analysis is performed on the original bracket to observe the stress distribution in the part. Fig. 12 shows the von Mises stress distribution for all the load cases. The areas shown in the blue color of the part replicates the inefficient use of material. This represents the negligible effect on the performance and still having the scope to optimize the geometry. Note: the final design satisfies yielding condition with safety factor from 1.1 to 2.26. Conclusions: this paper has discussed the significance of using the Inspire Optistruct software for design optimization and suitability for additive manufacturing process with a proper case study. The stress margin was within the yield strength and the weight reduction percentage was 70%, 6.8 pounds to 2.0 pounds. Further research may be required on other gas turbine parts. Acknowledgement: the case study developed as part of an initiative taken at IJERT Ltd on additive manufacturing workshop with IIT Hyderabad and EOS Germany. Images are prepared by IJERT for illustration purposes only. Does not contain any customer information. References: Fig 12. Stress plots at different locations of bracket. Note: the maximum stress developed is 40.31 ksi, which is well below the yield stress of 128 ksi. The redesigned part has to sustain the same loads while fulfilling the same design requirements. The von Mises stress developed should be lower than the yield strength. Structural analysis has been carried out by using ANSYS software. As shown in Fig. 13, the redesigned part satisfying the strength requirement for all load cases. 1. Brook, Rose. Additive manufacturing can lower aircraft building and operating costs. TCT Magazine, October 29, 2013, www.tct-manufacturing-3D-printing-news/additive manufacturing can lower aircraft building and OPR. 2. Zhu Jhgu XJ Zhang WH and Beckers P. Structural design of aircraft skin stretch forming die using topology optimization. Journal of Compute and App Math, 2013. 246, p. 278-88. 3. Deaton J.D. and Grandy R.V., A Survey of Structural and Multidisciplinary Continuum Topology Optimization, Post 2000. Struct and Multidiscus Optim, 2014. 49, 1p 1-38. 4. Bensi, M.P., and Kikuchi, N. Generating Optimal Topologies in Optimal Design Using a Homogenization Method, Computer Methods in Applied Mechanics and Engineering, Volume 71, Number 2, November 1988, pages 197224. 5. Schimmels, G.H., ng.wd, and mod, hf, 2017, October. A comparative study on stress and compliance-based structural topology optimization. In IOP Conference Series, Materials Science and Engineering, Volume 241, Number 1, P012003. IOP Publishing. 6 Adamski, Volodymyr, and Janusz Michalswas. Development of methods for designing and manufacturing aircraft components with additive technologies. Mechanic 93.3, 2028-14. 7 Additive Manufacturing Solutions and Industrial 3D Printer by EOS. EOS.info, 2021, https://www.eos.info/n. 8 Aerospace Metal Distributor. ASM Aerospace Specification Metals, Inc. Florida Aerospace Metal Distributor, www.aerospacemetals.com/index.html. 9 Autodesk Community. Autodesk Community, forums.autodesk.com/autodesk. 10 Brooke, Rose. Additive manufacturing can lower aircraft building and operating costs. TCT Magazine, October 29, 2013, www.tct-magazine.com/3d-news/additive-manufacturing-can-lower aircraft building and Fig 13. Stress plots at different locations of redesigned bracket IJERT 10 is 060013 www.IJERT.org 128. This work is licensed under a Creative Commons Attribution 4.0 International License.